So I will skip the intros in the title slide. So as we're all aware, at IEEE Sensors, we live in a world of sensors, some of which are remote sensors, which we want to put in locations that are difficult to reach, and they require wireless transmission or some power or some sort of remote energy. Such examples may be like agriculture, where we're interested in soil moisture and nutrients below the ground, the quality of the plants, and also there's city and safety planning like vehicle detection, air and water quality, structural integrity such as this sensor on the bridge. And just recently, the FDA has approved a implantable glucose sensor for up to 1 year that wirelessly transmits to a base station. So we know for these remote sensors, they have some problems, like we can't embed these sensors where battery replacement is impractical, and distribution of large amounts of sensors requires a replacement of large amounts of batteries, and that's also impractical. So the concept of a passive remote resonance sensor is not completely unprecedented. One very famous example has been when the Soviet spies, they put a resonant cavity inside the US seal, and they put it in the US embassy in Moscow. And so it had no battery, was powered by an external RF signal. It went undetected for almost 7 years. And the way this worked was that there was an antenna which received some RF energy, a resonant cavity with a metallic membrane which vibrated with sound waves. And so the reflected RF energy was modulated by the sound waves, and they were able to basically listen to exactly what was being said. And the device was completely passive and could basically stay there forever. And was very hard to detect because it did not emit RF frequency unless it was being read. And just recently, there's been a demonstration of an electrodeless quartz crystal resonator. However, the problem is, since it doesn't really have a nice antenna, it was only operationally demonstrated at 3 millimeter distance and required a very high power RF signal. So in this work, we propose a more practical solution to interfacing with the quartz crystal resonator. So the quartz crystal resonance sensor has been extremely successful and extremely popular. It's commonly used in a thickness shear mode, where the motion is perpendicular to the electric field in the device. And its resonance frequencies that can be determined by this equation here, which is a function of the thickness of the resonator, the shear elastic constant, and the density of the quartz. And it has been so successful because of its extremely high Q and very stable resonance. So this allows the functionalization of the quartz with enzymes, antibodies, many different functionalizations, which result in a heat or mass loading, which shift the resonance frequency. Also, lots of physical sensors have been demonstrated too. It's also known that the quartz device can be modulated by a force. So it's been shown that in a quartz cantilever, a very small force can lead to large shifts in the resonance frequency. So we use this force frequency phenomenon to make our Magnetoflexoelastic Magnetometer. The basic principle of operation is you have a unimorph with quartz and a magnetostrictive material. When the met glass, the magnetostrictive material, stretches, it induces a deflection in the quartz and thus a strain. And due to the stress, the modulus is affected, and therefore the resonance frequency shifts. To fabricate this device, we start with 100 micron thick AT cut quartz. Using lithography, we generate an nickel electroplating. We make a 15 micron thick hard mask, and we do argon and SF6 dry etching to etch down to about 19 microns, make a very high frequency quartz. And then we strip the nickel hard mask off. Then it's a simple matter of chrome gold evaporation and patterning to make the top electrode. The device is flipped over, and we do our bottom electrode chrome gold, and then we sputter Ti, met glass, and our source target is met glass 2605 SA1, followed by Ti gold. The Ti is there for adhesion promotion. The gold is for corrosion prevention. Finally, we do a fib cut to make this into a cantilever shape. This is roughly 500 by maybe 750 micron size cantilever. And so then to realize the wireless implementation of this, we connect a loop antenna to the quartz crystal resonator, shown here. And then we connect another matched loop antenna to a network analyzer with a tuning capacitor. A Helmholtz coil is placed around the device to provide controlled magnetic signal to test the magnetometer operation. And we choose a loop antenna because it's relatively simple to construct. It has a well-known radiation pattern. It's very similar to a dipole. And using this kind of device with a single broadband detection, we can detect many quartz crystal resonators. However, the downside is that there's a rapid signal drop-off with distance, which I will talk about more in this presentation. So if we look at the S11 and phase versus frequency of this device, we see a relatively low Q resonance coming from the loop resonance, about 200. And then there's a very high Q coming from the quartz crystal resonator. And it should be noted that using this, you can very easily track the center resonance frequency of the quartz crystal resonator and through phase or magnitude. And it could be because the quartz crystal resonator is a much higher Q of about 6,600. So to confirm that the device is operating as we expect, it's working through a magnetostrictive phenomenon, I point you to a very typical magnetostrictive curve, which is obtained by sputtering the met glass onto a glass cantilever and measuring the deflection with a laser vibrometer with an applied magnetic field. So what you see in low fields is a cutoff region where very little strain is created, then a linear region, and finally a saturation region. If you look on the left, where we track the center resonance frequency shift versus applied field, for both the wired and wireless case, that is, we just took off the loop antenna, connected it directly to the network analyzer, we see the same sort of response. And so it's very consistent with the physical response measured by the laser vibrometer, and so can confirm that it is magnetostrictive in nature. So if we look at this device by modulating the separation distance between the two loop antennas, we see the same sort of characteristic in all distances, from 0 to 45 millimeters, as we measure the center resonance frequency shift versus applied field. And you'll notice that at 45 millimeters, the data is quite noisy, and this is about the limit of R set up to detect this. So to look at the effect of separation distance more closely, we look at the S11 versus the frequency for the different separation distances, and I zoom into this region. You'll notice that the resonance frequency does not shift with distance. And so if we then model this using the Butterworth-Van Dyke model, which is a very common model for quartz crystal resonators, you look at the parallel resonance frequency equation and the series frequency equation, you see they're comprised of entirely the reactive components. And so we propose that this can be modeled entirely with the RF loss resistive component by adding it to this model. So to extract this, we do an we do a S11 fit by 2 3-parameter Lorentzians, 1 Lorentzian for the loop resonance, 1 for the quartz crystal resonator resonance. And from that, you can get your measured Q. And since the Q of the device itself is not affected by the RF energy loss, just you can basically extract a separate resistor, RF loss resistance, and model that with distance. And so as we see, as we expect, it increases exponentially with distance. And then further on, we want to see how this device operates in terms of its sensitivity. We look at its limit of detection. So to do this, we look at the shift in phase, because it's a bit more sensitive than the shift in resonance frequency. We apply a relatively low frequency, half-hertz square wave on our Helmholtz coils, and we can see the modulation visually very easily, down to about 20 microtesla. You can see the black line. It's oscillating with a square wave. And then if we want to push the sensitivity a little bit further, you can do an FFT. And in this FFT, for both the wired and wireless case, you can just barely make out a 7 microtesla signal is what we applied in this case. You can just barely make out the shift here, this peak at half hertz. For the wired, it's actually higher, and you can even see some subharmonics. And this is, all because of the RF energy loss and inefficiencies from that. And so wired signals down to about 1.5 microtesla can be resolved, whereas around 7 microtesla were resolved wirelessly by the FFT. So in conclusion, we've demonstrated a passively powered, with no batteries, operation of an 86 megahertz quartz crystal resonance magnetometer, and demonstrated and confirmed that it was magnetostrictive in nature. We demonstrated operation down to about 45 millimeters, and we modeled the increased separation distance as a result of an RF energy loss resistor in the BVD model. We were able to measure magnetic fields as low as 7 microtesla wirelessly, 0 millimeter separation distance. And so in the future, if we used, say, highly directional transmit and receive antenna pairs instead of loops, we should be able to increase that distance and have better sensitivity. And based on the electrode list results, it would also be interesting to do highly directional transmit-receive antenna pairs with the QCM in the propagation region. And it should also be noted that this concept is very modular. I mean, you can basically take any quartz crystal resonator, functionalize it, and connect to this loop antenna and operate it passively and remotely. And so I think it hopefully will be very interesting to see what other people might be willing to do with this. So finally, I'd just like to thank our funding partner, NSF, and all the organizations that helped this project along. And hopefully I can take some questions.